Hello and welcome to today's class. For this class, we'll try to consider, or perhaps we'll start discussing about a course called Strength of Material. So we'll start this study of this course from the crash. So here is simply our first video on the study of strength of material. So we'll look at the study of strength of material and other aspects involved in the study of strength of material, like your shear force, bending moment, and stress, strain, etc. Right? Center of gravity, a lot. Right? So let's start with the study of strength of material. By definition, strength of material can be defined as the analysis of the interaction between the externally applied load and the internal generated forces of adhesion and cohesion. That's your definition for strength of material. When it comes to the study of strength of material, there are some terms we need to be familiar with. So in the study of this course, there are some terms we need to be familiar with. What are these terms? Let's discuss these terms one after the other. Let's look at some basic terminology in the study of strength of material. There are about 6 to 5 basic terminology we need to be familiar with in the study of this course. So let's start with the first one. They're called the number one. The first terminology there is called rigidity. Let's consider the first terminology called rigidity. By definition, rigidity can be defined as the ability of a material or object or a body to resist deformation under the applied force / load. That becomes your definition for rigidity. Now, the concept behind the word rigid and non-rigid body, what's the difference between those two? For rigid body, the task there is that, let's say I have a bread, for instance. I have a bread in this way. I apply a block, let's say a building block, something of this nature, on a bread. What do you observe? The bread will what? Deform, right? So that bread is what? A rigid body. But let's say I have a block in this form and I place a marker on it. Nothing will happen to the what's it called, to the block. Hence that block becomes what? A non-rigid body. That's your first terminology in the study of strength of material. Rigidity, the ability of a body to resist deformation under the applied force / load. Let's look at second terminology in the study of this course called elasticity. Let's look at elasticity. This can be defined as the ability of a body to regain its original shape and size after it has been distorted by an external force. That becomes your definition for elasticity. So, I understand definition of elasticity. What does it mean? The ability of a body to regain its original shape and size after it has been distorted by what? An external force. That's elasticity. So for a body to be in elastic state, it means that after expanding that body we expect that body should go back to its original shape and size after it has been distorted by that force, right? So that becomes your second terminology in the study of strength of material. Let's look at the third terminology. The third terminology here is simply force. Force. Let's consider the third terminology called force. What's force? By definition, force can be defined as anything that changes or tends to change the position of a body either at rest or in motion. That becomes your definition for force. And note that force is abbreviated by F. and the SI unit for force is what? Is Newton. So know that force is measured in what? In Newton. So that becomes your definition of force. All right, that's your third terminology. Let's look at the fourth terminology in the study of strength of material called stress. Stress. Let's discuss stress, please. So in the study of strength of material, stress is one of the important terminology we need to familiar with. So by definition, stress can be defined as the force acting per unit area of a material or an object if you want to. So it's not that stress is represented by a Greek symbol called sigma. This becomes sigma, a Greek symbol, for representing stress. So not that sigma is a Greek symbol used for representing stress. So I'm saying that stress is simply the ratio of force to each area of a material. So and stress is represented using a Greek symbol called sigma. So mathematically, I'm saying that stress sigma is equal to force all over area. Let's get SI units. Force measured in Newton, area in meter squared. So I'm saying that the SI unit for stress is given as what? Newton per meter squared. So note that the SI unit for stress is given to be what? Newton per meter squared. So we have looked at rigidity, elasticity, force, stress. Let's look at the fifth terminology called strain. Fifth terminology called strain. Strain is simply the fifth terminology in the study of strength of material. By definition, strain can be defined as the ratio of deformation of a material to its original length. So I'm saying that, it is represented by a Greek symbol called epsilon. Observe, epsilon. Epsilon. So this note that stress is abbreviated using the Greek symbol sigma. Sigma. While strain is what? Epsilon. So I'm saying that mathematically I'm saying that strain is equal to what? Deformation all over what? The original length. So note that strain can be defined as the ratio of deformation of a material to its original length. We know that deformation is when something changes dimension, as is measured in what? In meters. Also, length is what? In meters. Meter cancel meter. Hence, note that strain has no SI units. Very important. Note that strain has no SI unit. This becomes your concept in the study of strength of material. Let's look at one last one called deformation, which is the sixth terminology in the study of strength of material. Let's look at deformation. What's deformation by definition? By definition, deformation is simply the change in the physical dimension of a material. When dimension change its shape or size, deformation has occurred, right? So the task is that if I have this marker this way now, this marker has its original length. But if I elongate it, if I extend it this way or compress it this way, there's no how this marker will change what? Its original dimension. So by definition, we said Deformation can be defined as the change in the physical dimension of a material. At this point now, let's look at types of deformation that we have. All right, at this point here, there are two types of deformation. Number one, we have the elongation, and number two, that we have the contraction. These are like the two types of deformation that we have. We have the elongation deformation, and number two, we have the contraction deformation. Let's look at this one after the other. Let's have the first one called the elongation. So by the word elongation, to elongate something. So elongation can be defined as the increase in length of a material. So when a material increases its length, deformation has occurred. So the ability of a material to increase its shape or size, that becomes what? Elongation, right? Also, number two, that's called the contraction. This is the first one. Number two, that we have the contraction. So by definition, this is simply the ability of a body to reduce its shape and size. So when a body is being extended in this pattern, that becomes elongation. When a body is being compressed, that becomes what? A contraction, right? So like there are two types of deformation that we have. We have the elongation and what? The contraction. Both these two are still under deformation. These two will always change the dimension, right? So that becomes your tax under this study of strength of material. So those are like the 6 basic terminology in the study of strength of material. At this point, at this stage, what we have now, let's look at Hooke's law. Let's look at Hooke's law. Now, let's look at Hooke's law. Hooke's law can be stated in two ways. For your basic level, for your junior secondary level, Hooke's law can be stated in terms of force and extension, right? Also, Hooke's law can be stated in terms of what? Stress and strain. That's what the stress and what the and strain. Let's look at these two, one after the other. Let's look at Hooke's law, number one there. Hooke's law in terms of what? Force and extension. Let's look at Hooke's law in terms of force and extension. Hooke's law in terms of force and extension states that provided the elastic limit of an elastic material is exceeded, the extension E is proportional to the force causing it. So what do I mean? I'm saying that, look up please, from what I just stated, I said that I mentioned extension before force. I said that Hooke's law can be stated in terms of force and extension, and it says that whether the elastic limit of an elastic material is exceeded, that the extension E is proportional to what? To the force causing it. So I mentioned extension first before force. So I'm meant to be having E that is proportional to what? To F. But this is not correct in this pattern. But the mathematical approach mathematically, I'm saying that force now is very proportional to what? Extension. From my definition, extension was the proportion of force, but mathematically, force is the proportion of extension. How come is it force to extension? Why is it not extension before force? Because from my definition, extension came first before force. How come in my mathematical expression I'm having force before extension? Here's the tax, here's the idea. There can never be an extension without force. An extension cannot occur without a force. So there must be a force applied first before what? An extension can take place. Look at my camera looking at me now. Let's say nobody's beside the camera now, and the camera starts walking towards me. I'll have to run away because there's no force applied to the camera. So the camera has to be what? There should be a force that must be applied to before what? An extension can what? Occur. That becomes your This becomes the mathematical expression for Hooke's law. So in mathematics, how do we take off proportionality sign? We introduce a constant k and equal to a constant k. So for me, I'll have that f is equal to ke, right? At this point, let's make k subject. So k now is equal to f over e. This k is called stiffness of spring, or call it spring constant, right? We want to, let's call it stiffness of spring or spring constant. F here is force and E is your extension, right? So note that force A, Hooke's law, can be stated in this condition. Also note that Hooke's law again can be stated in what? In terms of stress and what? Strain. Let's look at that, please. Let's look at Hooke's law in terms of stress and strain. Let's look at Hooke's law in terms of stress and strain. Number two, in terms of what? Stress and strain. Hooke's law in terms of stress and strain states that the strain in an elastic material is proportional to the word stress causing it. So mathematically, stress is proportional to what? To extension. From here now, I'll introduce an equal to a constant. That becomes stress now is equal to, my constant here was k. Now my constant here is not k, rather E. I have capital E, then what? Extension. So let's make E subject. So I'm saying that E now is equal to what? Stress over strain divided by extension. I have that E is what? Stress over strain. What's E? This E is called the Young's modulus, please. This E is called the Young's modulus. So Young's modulus now is equal to what? Stress over strain. This becomes like the tax behind Hooke's law in two cases, case 1 and what? And the case 2. At this point, let's do a little bit of manipulation and let's see what we get. At this point now, we know that, but we said stress was what? Force over area. Also, we said strain was what? Deformation over original length. So note that deformation is what? Is change in length, right? I can say it's change in length. This one is for representing deformation, right? So I have deformation over what? Original length, L, right? So at this point now, putting this stuff here, what do I get? E is equal to what? Stress, force over area, divided by what? Strain, change in length over original length. So permit me, please, permit me that let's say change in length to be E. So change in length can be either what? Either increase or decrease. And increase and decrease signifies what? Extension, right? Extension. So this I can swap this one as being this, or this as being this. So at this point then, what do I get? All right, for me, I'll have that E, Young's modulus, is equal to force over area divided by change in length, which is E now. We said should be E over what? Over original length. From here now, E is equal to F all over A times, this becomes first over what? Over E. Combine these two, E now is equal to what? FL all over AE. Make this E subject. That becomes extension E is equal to, I will swap these two. Swap it. That becomes FL all over A capital E. So it becomes your formula for calculating extension of a material. Please note these formulas Very, very important, please. Very, very important, please. So, and this becomes your, note that extension is measured in meter, please. Extension is measured in meter or perhaps millimeter. It depends on the question. So this becomes your mathematical expression for calculating extension. Let's look at one example and next class one, and we'll look at several concepts in our next class. In our next class under the study of strength of material. Let's look at example one. Welcome back. Let's look at this example and let's see what we get. The example says that a square steel rod 40 millimeter by 40 millimeter is used to carry an axial load of 200 kilonewton. Calculate the shortening in length and shortening in length of 100 millimeter if the Young modulus is 4.28 times 10 to the power 8 kilonewton per meter squared. How do we get this done? First, your first task in science is to list out the givens. Right? What are we given in the question? One says that a square steel rod 40 millimeter by 40 millimeter. The word 40 millimeter by 40 millimeter, it signifies what? Take a little bit and think. What does this signify? 40 millimeter by 40 millimeter. What does this signify? It signifies what? The dimension. Not because of your area, right? The area there. So I'm having area has been equal to, which is A, sorry, has been equal to what? 40 millimeter by what? 40 millimeter. Please, it's not 40 times 40, it's 40 by 40 millimeter. Is used to carry an axial load of what? 200 Newton. Kilonewton. That's my force. I'm giving force or load, perhaps, if you want to. I'm giving load, L-O-A-D, load. You can measure load in terms of P or F. Let's use F here, right? It's what was my load there? 200 kilonewton. Let's stop. Calculate the shortening in length of 100 millimeter. Listen to the question. It says, calculate the shortening in length of 100 millimeter. Please, that 100 millimeter, is it the value for shortening length or length, original length? Think. So it says calculate the shortening in length of 100 millimeter. I'm asking now that, is that what's it called? The value 100 millimeter, is it for shortening length or original length? Of course, the value there is for what? Is for original length, because I was supposed to calculate what? Shortening length. So my original length there, L, is what? 100 millimeter. So question says find what? Calculate shortening length. That's change in length. Calculate what? My E. That's the meaning. I'm looking for E. Change in length. Right? So shortening length is like decrease of length, like the decrease. So we said either increase or decrease. E represents it. So I'm looking for E. Is unknown, right? So if Young modulus, I'm given Young modulus E has been equal to 4.28 times 10 to the power 8 kilonewton per meter squared. All right, let's get this done, please. My very first task here is quite simple. My task now is that I will try to after listening to parameter in science, what's the next task? Check, are you converting? Right? Are you converting? Oh, of course I'm not converting. Why? I'm having meter, millimeter, millimeter. I have to convert. Kilonewton, no conversion for that. But this is meter, millimeter. So which one will I go with? Of that, my young modulus here is going with what? Meter. So hence, other units what? In meters, please. So let's convert them. For my area now, A, 40 millimeter to meter, that's 0.04. So convert this one first. That's 0.04 millimeter multiplied by what? 0.04 millimeter, right? So by dividing what I get there, my area now is equal to, multiply the two, I'll have 1.6 times 10 to the power minus 3 millimeter squared, right? Millimeter times millimeter squared. This time this will give this. So it becomes your area, converted value for area. Also, we need to convert our length. My length L is given to be what? 100 millimeter. Convert to meter. That becomes what there? 0.1. So I have 0.1 as my meters, as my converted value for the length. So now let's put in our values and let's see what we get. So we said calculate what? Shortening length, right? Right. So we know that recall that we said E is equal to FL all over AE. Check. Am I given force? Of course, force is given 200 kilonewton. Am I given length? Of course, length is given as being equal to 0.1 meter. What's area? That's 1.6 times 10 to the power 3 minus 3. What's E? This value here. So let's get our E. From there now, my extension E, or perhaps shortening length will be equal in value to, from there we'll have that E is equal to, what's force there? Force F is what? Force 200. I have 200 multiplied by what's length? My converted value is 0.1. So I have 0.1 all over what's my area? That's 16 points. That's 1.6 times 10 to the power what? Minus 3 times what's my modulus? That's 4.28. 4.28 times 10 to the power what there? 10 to the power 8. So I have this. So from here now, what's my E? Extension now E is equal to, let's punch this and let's see our value, please. Multiply numerator, I have 200 times 0.1. I have about 20. This is 20 all over. Multiply the numerator, that becomes 1.6 times 10 to the power minus 3. So times 4.28 times 10 to the power 8. So I have about 684,800, right? Which is equal to, divide 20 by this. So therefore my extension E now is equal to 20 divided by 684,800. So I have about 2.92 times 10 to the power minus 5 meters. Is it meter or meter? That's meters. So it becomes my answer to that particular question. So it becomes my answer to this particular question. Let's look at one last thing before we proceed. Look at one last thing before we end this concept. One last thing. Let's look at type of stress. Let's look at the types of stress. Then we're off. Let's look at type of stress. So there are two types of stress. We have the tensile stress and compressive stress. Let's discuss the type of types of stress. We said there are two types of stress. Number one, there we have the tensile stress. Number two, we have the compressive stress. So these are like the two types of stress we have. Let's start with the first one, called the tensile stress. All right, definition please. Tensile stress is simply a stress that tends to pull a material, thereby increasing the length of that material. Tensile stress is simply a stress that tends to pull a material, thereby increase the length of that material. So for tensile stress, let's say I have a figure, a diagram in this form, right? For tensile, my arrow is going outward. Observe, oh, my arrow is what? Going outward, because I'm tensile and what? I'm increasing the length, right? That's tensile. So if I draw this material, what will happen? Observe that I'll have something of this nature. If I draw this material now, this original material now, if I elongate it, if I what's it called? If I try to draw it, observe that the length will increase, while the height is also what? Decrease. So for tensile stress, the length increases while the height becomes shorter, right? That becomes your tensile stress. So a stress that tends to pull or pull a material, thereby what? Increasing what? The length of that material. And notice that for tensile stress, the arrow are going what? Outward. Let's look at the second one, called the compressive stress. Definition, please. Compressive stress is a type of stress that tends to reduce the dimension of the physical dimension of a material. So for compressive, there, the task is that you are reducing it. For tensile, you are what? Trying to what? Increase the length. For compressive, what? Decrease the length of that material. And let's consider a diagram this way. Let's say I have a diagram this way, right? And I have my arrow compressing this, a force compressing this, another force compressing this way. All happen this way. Observe something of this nature. Observe about something of this nature. Something of this nature. I will end up having something of this nature. So for tensile, for compressive, the arrow are going inward. For tensile, outward. Number one. Number two again, like for tensile, the length increases while the height becomes shorter. For compressive, the length decreases while the height becomes higher. That becomes like your concept to note under these two types of stress. There are compressive and what? Tensile stress. Next class, look at some problems under this. Then we'll proceed to the study of shear force, benefit, and what have you. All right, see you in the next class. Do well to share this tutorial course to your friends and classmates that are offering this of material. So thank you for watching and welcome to Excellent Link Academy. See you next class. Stay tuned. Do well to follow us on our TikTok page, Facebook page, and Instagram page. I'll drop the link to those social media platforms in the description of this video. So join us together and learn with us. Thank you very much. Welcome to Excellent Academy once again. See you in this class.